Today we're going to talk about matrix differential equations with complex eigenvalues. So here's an example problem. X prime is equal to the matrix -1, 4, 1, -1 times x, and we're also given an initial condition of 4, -3. First step, we need to find the eigenvalues. So to do that, we say determinant of the matrix -1, sorry, this is -4 right there, -4, 1, -4, minus lambda times the identity matrix. And we have to find that when the determinant is equal to 0. So then we use a characteristic equation, -1 minus lambda times -1 minus lambda minus -4 times 1 is equal to 0. Then when we multiply and FOIL things out, we get lambda squared plus 2 lambda plus 1 plus 4 is equal to 0. But then what we notice is we can factor out. We can get lambda plus 1 squared. We move 4 to the other side, -4, and then we can solve for lambda, and lambda becomes -1 plus or minus 2i. Then to get the eigenvectors, you have to plug in one of these complex conjugates. So there are two complex conjugates. I'm gonna pick, for sake of ease, I will pick the negative solution. So I will pick -1 minus 2i. Then I'll plug that back in to -1, 1, but this time I'm going to subtract. I'm going to subtract -1 minus 2i. 1, I don't subtract anything from the off diagonal terms. And then -1 minus -1, sorry, -1 times -1 minus 2i, and then I have -4 over here. When I simplify it, I get 2i, 1, -4, 2i. Now what I need to do is find the appropriate eigenvector. The eigenvector is also going to be a complex number. So I'm just going to look at these two terms, and I'm going to say, this row, if this row is 1 and 2i, then my eigenvector must be 2i, -1. Let's check if this is true. If I multiply 2i times 2i, I get -4, and if I multiply -4 times -1, I get +4. -4 plus +4 is equal to 0. This means that we have found the correct eigenvector. And this also shows that we found the correct eigenvalue. Now, the reason I chose one complex conjugate of my two eigenvectors, and I only evaluated the matrix A minus lambda I at that one eigenvalue and found one eigenvector, was because you only need one complex conjugate, one of the two eigenvalues in the complex conjugate pair to actually get your solution. So here's what you do. You say x is equal to e to the eigenvalue that we chose. This is very important. Take that eigenvalue. It's -1 minus 2i, multiply it by t, and then multiply it by the eigenvector that we found. So we get 2i minus 1. Then what we do is we separate the real and imaginary parts in the complex exponent. So we get e to the -t times e to the -2it times 2i negative 1. This is where we need something known as Euler's formula. So Euler's formula says e to the I theta is equal to cosine theta plus I sine theta. So here what we have to do is say x is equal to e to the negative t times cosine of 2t. Here I'm going to put a minus because cosine of negative 2t, so really this would be negative 2t, theta here would be negative 2t, but cosine of negative 2t is equal to cosine of 2t, so I'm making that simplification right away. Then I sine, negative I sine of 2t, if I had just put in sine of negative 2t, we know that sine of negative 2t is negative sine of 2t. So I put the negative here. And I multiply it by the corresponding eigenvector. Now, what's the goal from here? The goal from here is to separate the imaginary and the real parts. So we multiply it out. And we get the following. Notice I'm going to keep the e to the negative t term on the outside because if I don't, this gets very annoying to deal with. But when we multiply things out this way, we just separate imaginary and real components. So I'm just going to get the real parts first. Cosine of 2t, so how about this? Cosine of 2t times 2i cosine 2t. Then I do negative I sine 2t times 2i, so I get plus 2 sine 2t. Then you get, for the second entry, you get negative cosine 2t minus, or actually plus, sine I sine 2t. We separate the imaginary and real parts out. So when we do that, and I'll use a separate sheet for this, we get x is equal to e to the negative t times 2 sine 2t minus cosine 2t plus I times 2 cosine 2t and sine 2t. Then what we figure out is that there are actually two independent components here, correct? So there's an imaginary component and there's a real component. The imaginary and real components each individually give you your separate answers. So we want to rewrite this as x, your solution, is equal to c1 e to the negative t times 2 sine 2t minus cosine 2t. Then, by linear combination, we add c2 times e to the negative t times 2 cosine 2t sine 2t. This gives us the linear combination we care about. So we take a linear combination of the real component and the imaginary component. Then we plug in our initial conditions. So we knew that our, just to remind you, x evaluated at 0 is equal to 4, negative 3. So what we'll do is we'll do the same here. So x of 0, so we know 4, 3 has to equal e to the negative t is equal to 1 at when t is equal to 0. So I get c1 times 2 sine of 2 times 0, 0. And then negative cosine of 0 is going to be negative 1. Plus c2 times 2 and then 0 correspondingly. So then when we solve for this, we get 2c2 is equal to 4, and c2 is equal to 2, and we get c1 is equal to negative 3 because negative c1 is equal to 3. So this gives us our c1 and c2, and that means our overall solution is e to the negative t times, and this is after we add everything together, we get negative 6 sine 2t plus 4 cosine 2t minus 3 cosine 2t plus 2 sine 2t. This is our final answer after we plug in initial conditions. Now you might ask, how do we actually figure out how to graph this? So first of all, the first thing you need to know is that this solution is, we need to review what the eigenvalue actually was. So as you can see, our eigenvalue was negative 1 plus or minus 2i, or eigenvalues are negative 1 plus or minus 2i. That the real part tells you if it's stable or unstable. So let me rewrite this on a separate sheet of paper. The eigenvalues we got were negative 1 plus or minus 2i. The real part tells you stability. The imaginary part doesn't really give you any information. It just tells you that if there is an imaginary part, if imaginary part exists, there's some kind of rotation involved. Okay? So when we try to graph this, we know that starting at some point, there is going to be, or actually, if we start from a point away from the origin, our solution will spiral into the solution, like so. However, one thing is people ask, okay, how do you know it's this answer versus an answer like this? There's a very different nature to this one. Notice that it's counterclockwise. Actually, I drew this poorly, but you can tell that this has a different rotation. This is clockwise. This is counterclockwise. How do we know if it's clockwise or counterclockwise? These aren't actually the solutions. These are just different. We're still trying to figure out how we actually graph this. So what you do, and this is very simple, if you look at the original equation, it's negative 1, 1, negative 4, negative 1, x. So what we're going to do is we're going to say if this is, if we're on the x-axis, we're anywhere on this x-axis I'm tracing out over here, and let's say I pick the point x is equal to 1, 0. So that's a point on the x-axis. What I can do is I can plug in that value here, and then what you notice is that x prime ends up becoming negative 1, 1. So this is important. What does that tell you? So it tells you that the derivative is going to point in this direction, in the negative 1, 1 direction. So this actually tells you that our solution is actually so this is our 1, 0 location. This vector is negative 1, 1. We also know that this is a stable spiral. So what this says is that the derivative points in this direction. And then we know that's a stable spiral, so we know that our answer looks something like this. So that tells us if our answer is clockwise or counterclockwise. Look at the derivative at 1, 0. You know that 1, 0 gives you just the first column of this derivative matrix. And then we know which way the solution will go from that point. We also know that the solution is stable, so everything will go towards that origin, and our graph, the graph of our solution, looks something like this. So for our second problem, we have x prime is equal to 2, -5, 1, -2 times x. Our initial condition is given as x of 0 is 3, 2. We want to find the eigenvalues, so we say determinant of 2, 1, -5, -2, minus lambda I is equal to 0. So again, this is a determinant of 2 minus lambda, 1 minus 5 minus 2 minus lambda is equal to 0. So then we do our determinant. We do 2 minus lambda times -2 minus lambda minus -5 times 1 is equal to 0. We get lambda squared minus 4 plus 5 is equal to 0. We get lambda squared is equal to -1. So lambda is equal to plus or minus I. It's a pure imaginary solution. So what we do is so this is A, this is our A. If we do A minus lambda I, we'll get 2 minus I, 1, -5, minus 2 minus I. Now what we're trying to do is figure out what the appropriate eigenvector for this would be. So we want this to equal, so we want A minus lambda I times the eigenvector to equal to 0. So if we look at this, and we look at, let's say, the second row, our guess is that V is equal to 2 plus I and 1. Now let's check this. So if I multiply 2 plus I times 2 minus I get 2 squared plus 1 squared, so I get 5, and I multiply -5 times 1, so I'll get 5 minus 5, which is equal to 0. So the second component, so if I multiply this vector out, the first component will be 0, and the second component, if we multiply out, that's how we got our eigenvector, that will equal 0. So we get, when we multiply this to A minus lambda I, we get 0 like we wanted. Now what we have to do is plug in to the following formula. E to the lambda t times the eigenvector V, and we get E, and I'm actually picked, so for my lambda here, I picked positive I. Lambda is equal to positive I. Here, I'm putting I, t, because I picked the eigenvector, so I need to make that clear. My lambda, the lambda I picked was lambda is equal to I. I plugged that in over here, and I basically found the eigenvector for this matrix, for A, by using this matrix. I multiply E to the IT times 2 plus I, 1. Sorry. Yes, that's right. E to the IT times 2 plus I and 1, right? So then I use the Euler formula. cosine of t plus I sine of t times 2 plus I 1. So now when I multiply things out, I'll get 2 cosine t plus 2I sine t plus I cosine t minus sine t. And then for my second row, it's just cosine t plus I sine t. When I separate the imaginary and real components, I get when I separate the imaginary and real components, I get 2 cosine t minus sine t cosine t, right? Plus I cosine t plus 2 sine t sine t. Here again, I separate the imaginary and the real components. So my answer is actually C1 times this real component, 2 cosine t minus sine t cosine t plus C2 times this imaginary component. Remember, this is all because all of our solutions need to be real. So we were given an initial condition of x of 0 is 3, 2. So what we'll do is we plug in. We get 3, 2 is equal to C1 times. So if I do 2 cosine of 0, I get 2 minus 0, so 2, and then I get 1 here, plus C2 times, I get 1, and then I get 0. Right? So what I will do is I get two equations. I get 3 is equal to 3 is equal to 2C1 plus C2, and for the first entry, and then for the second entry we get 2 is equal to C1. So awesome, we got our first answer. So then we plug into this equation, we get 2 times 2 plus C2, so C2 will give us -1. So these are our two constants. When we plug back into this equation, our final answer will be Alright, and now how to graph this. So first of all, you know that our eigenvalue was lambda is equal to plus or minus I. That is those are pure imaginary eigenvalues. The real part is 0, so it's not stable or unstable. So what this tells you is that your solution should look like a pure rotation. Again, we're going to take the same method that we used last time to determine is it clockwise, counterclockwise, and I guess what's the general shape of our phase portrait. So our original matrix differential equation was 2, 1, negative 5, negative 2 times x. So again, if we make x equal to 1, 0, we know that x prime would be equal to 2, 1. And this just gives you, so I'm actually not plotting out our solution exactly, but this is just a way of knowing the direction that the curve, the solution curve, will go in if we're starting from the x-axis. So if we started at 1, 0, which we're not, we don't know in this case, but if we started from 1, 0, we know that our derivative would be 2, 1. And so we know the general direction is going in this direction. We also know this is a pure rotation. So there's some kind of ellipse, and it probably looks like this. Because the y component of the derivative is positive, we know that this is going to be a counterclockwise spiral. Not spiral, counterclockwise ellipse of some sort. So this is our trajectory. And it doesn't go to the origin because this is a pure imaginary eigenvalue. So here's our third problem with complex eigenvalues. X prime is equal to 1, negative 1, 5, negative 3 times x. And we're not going to go through a particular solution. We just want to find the general solution. So what we do is, again, we take, so this is a. We do determinant of a minus lambda I is equal to 0, right? So determinant of 1 minus lambda, 5, negative 1, negative 3 minus lambda is equal to 0. So when we do this determinant, we get 1 minus lambda times negative 3 minus lambda minus negative 1 times 5 is equal to 0. So then we do negative 3 plus 2 lambda plus lambda squared plus 5 is equal to 0. Then we simplify this characteristic equation that we have. Lambda squared plus 2 lambda plus 2 is equal to 0. I'm going to subtract 1 from both sides. I get lambda squared plus 2 lambda plus 1 is equal to negative 1. Lambda plus 1 squared is equal to negative 1. So our eigenvalue is lambda is equal to negative 1 plus or minus I. So now what we're going to do is we're going to evaluate a minus lambda I. We're going to try to find the eigenvectors now. So what we're going to do is I pick lambda is equal to negative 1 minus I. Here I decided to pick the negative imaginary solution. Again, it doesn't matter which one you pick as long as you're consistent. So I pick this eigenvalue. So when I do a minus lambda I for this eigenvalue, I get 2 plus I, 5, negative 1, 2 plus I, times v is equal to 0. Again, we're trying to solve for what v should be, right? So we decide v should equal to, based on what the first row is, it should be equal to 1, 2 plus I. When we do that, we need to check if the second, if this eigenvector holds true for the second row as well. So if we multiply this eigenvector, we see that the first row if we multiply this eigenvector through with the first row, we'll see it gives 0. But we need to also test that for the second row. So if I do 1 times 5, and then I do, sorry, there's a negative 2 here. If I multiply 1 times 5 and 2 plus I times negative 2 plus I get negative 5. So 5 minus 5 gives me 0. So that means that this eigenvector is correct. So that means now we have to actually plug in our eigenvector and eigenvalue. So let me do it on a separate sheet. So we know that x is equal to e to the lambda t times the eigenvector. Remember we picked negative 1 minus I for lambda, and then the eigenvector that we got was 1, 2 plus I. When we use Euler's formula, we get e to the negative t times cosine of t minus, so cosine of negative t is cosine of t, and minus I sine of t, because sine of negative t will be negative sine of t. And 1, 2 plus I. So then when we when we multiply everything out, we get, actually I'll put e to the negative t there. Sorry about that. Actually, let me cross that out. If I do x is equal to negative t, then I'll multiply this out. So I get cosine t minus I sine t. That's the first entry. And then the second entry will be 2 cosine t minus 2I sine t plus I cosine t minus, actually plus sine t, because negative I times I is positive. Then when we separate the imaginary and the real parts, we get e to the negative t cosine t plus sine t. Actually, let me just 2 cosine t plus sine t plus I e to the negative t negative sine t cosine t minus 2 sine t. So what we get for our general solution, remember our first solution is C1 times the real solution, e to the negative t cosine t 2 cosine t plus sine t plus C2 times the second solution, which is our imaginary solution. Mistake there. Sorry, ignore that second term, I will rewrite it. C2 e to the negative t minus sine t cosine t minus 2 sine 2t. This is our final answer. Now we want to graph it. So again, our eigenvalues were lambda is equal to negative 1 plus or minus I. We know that our original solution, so I'm not actually graphing any solution right now, I'm graphing a generic solution, let's say, that starts anywhere in the phase plane. I just want to show how you can determine clockwise versus counterclockwise in this system. So we know that x prime is equal to 1, 5, -1, -3, x. We didn't have an initial condition, so we don't have a solution, but if we were to pick a solution, we want to figure out what solution does that trace out. So first of all, this real component, again, the real component gives us the stability. Because it's negative, we know it's stable. Furthermore, let's say we picked x to be equal to 1, 0. That would mean that our x prime is equal to 1, 5. So if we draw the phase plane, and we're at this point 1, 0, then we know that our derivative would be upwards in this direction, 1, 5. This tells us that our solution is counterclockwise, but also it's stable. So that means it's going to finally crash into the origin. Now I'm going to go on to some slightly different problems. So in general, we'll have, let's say we have a matrix differential equation that looks like this. Lambda 1 minus 1 alpha. Sorry, I meant to say alpha. So the thing is, we're interested in how the phase plane changes for various values of alpha, and this is also called a bifurcation analysis. So first we need to figure out what the eigenvalues are. And this matrix that I did here is just, say this is A, this is A minus lambda I. So then when I multiply it out, I get alpha squared, alpha minus lambda squared minus -1 times 1 is equal to 0. If I move over to the other side, I'll get -1. If I square root it, I get when I solve for lambda, I get alpha plus or minus I. Now, I'm not actually going to go through and try to solve the eigenvectors. Those depend on the case, and that's not really what we're interested in. We want to know, how do our solutions change as we vary alpha? So what this says is, if alpha is equal to 0, let's say, we know that this is a purely imaginary solution. So we say that the origin is the center of cyclical behavior, meaning our solution neither approaches the origin nor goes away from the origin. It just continues on a cycle like an ellipse or a circle. If alpha is less than 0, we have something known as a spiral sink. We have a spiral sink at the origin. So what this means is that if alpha is less than 0, if it's less than 0, we have a negative real part for our eigenvalue. The origin is stable. So our solution will approach the origin in that solution. If alpha is greater than 0, then we have a spiral source. And all this is saying is that if we start near the origin, just a little bit away from the origin, our solution will spiral away from the origin from that point.